Alright, today we're going to look at Euler's method for solving a specific solution to differential equation. Euler's method is used if you can't find an implicit or explicit solution. You have an initial value. You can get a numerical approximation for your y value. And it's based on the fact that y2 minus y1 over x2 minus x1 is the slope. So it's based on the equation of a line. If I think of this, I could rewrite this in terms of Euler's formula, because y2, I could think of y2 as my n plus 1 and y1 as my nth y, so go from nth y to n plus 1 y, and x, we could think of x in terms of t. Well, that's going to be my next t value minus my previous t value, t n plus 1 minus tn, and that's equal to my slope. But my slope is my differential equation. dy dt is the slope, which is f of t y. And now, if you think about this, the difference in t's, we'll call that delta t. And so we can rewrite Euler's equation as yn plus 1 equals to yn plus f. So this slope here, I'm going to evaluate it at this step, t sub n y sub n and times delta t. So Euler's formula really is nothing but the equation of a line, or the equation for a slope. And we keep doing this process, and it's called an iterative process. And every time you do any kind of iterative process can be done on a program or using a spreadsheet like Excel. So graphically, what is going on here? Here's my function y, and let's say I am here at this point t naught y naught, and I want to go to some y value. I want to figure it out what it is. I don't know what the curve looks like. So I take the equation of a tangent line, I go up a step size, let's say to here. That would be t sub 1, and that step size is a delta t. And now I've approximated y1. At y1 now I have a different slope, kind of looks like this. So I have a line going parallel to that slope, an amount delta t, and up here at y sub 2. And I keep doing this process, so that's be t2, until I get to where I want to go in terms of y. Now you see there's a little error here, and that error depends on my size of delta t and the function and so on. So this iterative process, we can do this in Excel, and we're going to take an example of it in Excel. So the example we're going to look at is, let's say dy dt equals t plus y, and we're going to say y of 0 is equal to 1, and we want to know what y of 1 is equal to. So let's do that in Excel. So in Excel I have it set up here. I have a few columns, n, t sub n, y sub n, my slope f of t n, yn, and yn plus 1. My initial value of t is 0, y of 0 is 1, and then my initial y value is 1. And my slope here, it depends on my equation, which is t plus y. So that's equal to this cell. If you look at the formula here, equal to this cell plus this cell. And then what is y sub n? Yn plus 1. Well, that's equal to, remember, that's equal to the previous y plus delta t. So here's where I'm going to refer to this delta t as 0.1, but I'm going to put a little dollar sign around the letter and number to fix that reference. So it's yn plus delta t times my slope, and that gives me my new y value, times this one here. So that's my new y value. And then t sub n now, the next step becomes equal this previous t plus delta t. But I'm going to fix that delta t again because I want to keep referring to that in case I want to change the delta t. So now it's 0.1. My new y is equal to this previous one here. And these ones you can type this equation in again. Remember, it's going to be equal to t sub n plus y sub n. Now I could have just pulled this cell down below and get 1.2 as well. And similarly with this one, what is this cell? This is equal to, let's write it again, equal to y sub n plus delta t times this f of t sub n y sub n, which is 1.22, and I would have to fix that reference to 0.1. But again, if I did it correctly, I could just pull this down here, get 1.22. So now we've set up a couple of rows. It's easy enough to pull it down. And the number we're looking for is here, the y10. So we don't need these two. But this is my 10th value I'm looking for. So this is my estimation. So my estimation is y of 1 is equal to 3.18748. And that's Euler's method. Now I could be more accurate. If I make delta t smaller, I have to do more steps, and we could get more accurate to get the actual value. This differential equation can actually be solved, and we can see that this is actually not that accurate because the actual value is 3.4244366. So there's an error here, about 7% error in my estimation. Now we can get it a little bit more accurate if we use what's called a modified Eulers. Instead of just going along stepwise like this with the slope, we get these two slopes. When we take the average of these slopes, we get a better slope, and we keep doing that, and that's called the improved Euler's method.